So I'm Stephen Edwards, and I'm the boring one of the group. I nominally teach computer science at Columbia University, but really I cut my teeth on the 6502, and let's see, we were talking about things like, set overflow pins and so forth. With this guy, Bill Mensch, who you might have heard of, let's see, so if you hear Chuck Peddle tell the story, he was the guy who invented the 6502, but in fact it was Chuck and Bill and a whole host of folks here. So my plan here is I'm just going to ask Bill a whole bunch of leading questions, and at the end we'll let you ask some maybe less leading ones or something like that. But that's the goal. Now, there's a long story here and a lot more than one hour's worth. But Bill, I wanted to start in 1973 with this beautiful building. Can you tell me about this beautiful building?
Yeah, hi folks. That's where I started. Actually, that's not the building that I actually got started with as an engineer, but that's the Motorola Mesa plant. Now that's been scraped. It's a hazardous, well, it's not official hazard waste, but that plant is gone. But that's where we designed the 6800 and the PIA, and the PIA is what Woz used with the Apple I as the keyboard interface. But that's the Motorola plant that I became an engineer at.
And let's see, you started there in 1970.
I graduated from the University of Arizona in Tucson in 1971. And so I talked my way into getting a job at Motorola. And so I don't know if we want to get into any of the details, but I think that's
good
about
enough. I've got another picture to share with you here, and it's really the reason that we're all here today, right? It's this chip that you had designed, the 6820 PIA, right? This is everybody's favorite. Did it interfere with your grades? Maybe you want to explain what this is and why it's significant.
Well, that's actually, in some ways, that was more popular than the 6800. And in fact, there was one customer, NCR, in Colorado Springs, were buying 12 of these. Actually, Motorola forced them to buy a 6800, but they were buying 12 of them because Motorola says you can buy 12 of these, but you have to buy a 6800. So that PIA was the first bit programmable, pin programmable I/O chip. Intel, I don't know if Intel ever had one, but you could have those two ports, port A and port B, and then you could handshake. So you could tell the peripheral when you gave it some more information, and also the peripheral could tell the system when there's information available for it. So that was revolutionary. There's several patents I have on that chip. The layout itself was the first layout of any integrated circuit that was patented. And I've had patent attorneys say, so how did you do that? And well, I had a good patent attorney at Motorola, Charlie Hoffman. He applied for all but 2 or 3 of my patents. All of my patents were filed by a Charlie. So the Motorola patents, I have a couple there, that was by a Charlie. But anyhow, that's bit programmable I/O was a revolution, and there you have it.
Yeah, it was fun. In fact, I was looking at Lisa's exhibition, and she's got a Apple I number 1 or 2, whatever it is, or something like that. Number 1, yeah. And I hadn't realized that both of the big 40-pin packages were yours.
Yeah.
Somehow, that's a nice thing.
Yeah, it is. And Woz and I had one conversation here in Mountain View at the Apple, I think it was the Apple offices. And that's the only conversation I've ever had with Woz. I'd love to have another one, but he's a busy guy. And there you have it.
Yeah, neat stuff. Right, and so Bill would be probably famous for this chip and its prodigy and so forth, right? This is known as Gpio, and just about every chip in this room has some on it in one form or another, I would expect, and broadly following this general idea, from what I understand. But there were some other things going on at Motorola at the time as well. Let's see. Oh, this one has 1 less 2 in the number. Right. So this is a processor that Motorola came out. Well, let's see. This is Oh, this is a late one, 77. But that came out 73 or so?
74.
74, okay.
74. It was actually, the PIA worked the first time, and it came out in February. It happened to be my February 5th was my wife's birthday at the time. But anyhow, on February 5th is when we had working 6820 chips. But this had to go through a couple of rounds, but anyhow, it took them about a month to turn it. At MOS Technology, we could turn it in days, but at Motorola, it took about a month to turn it. So maybe the second or third rev, the 6800 worked.
Okay. Yeah. And what participation did you have with the 6800?
Well, I have several patents on it, but we shared patents. The circuitry, I designed the buffer system of the 6800, and all of the Motorola 6800 family of chips used my circuits. And I also designed the process control monitor that would monitor every wafer to make sure it was in spec based upon the parameters that we engineers needed to use. So they asked me, and so that was one of my responsibilities. I compared the actual in-lab test of the transistors and could extract the parameters that we'd use in our simulators. So I did a lot of work on, you could call it the periphery, but the main logic was done by others. And Rod Orgel participated in that, and he was one of the inventors of the 6502. By the way, there was a 6802, and that would be another story another time.
Quite. So with this fantastic success at Motorola, of course, it was time to change everything, right? And so I think that brings us to 1974 now. And so something interesting happened in 1974 to you, from what I understand. And it's going from one ugly building to another here. So what are we looking at here?
Well, that's the MOS technology plant. That's where they actually manufactured the chips. The vice president's office was the first two windows, I think, on the top there. So the engineers were on the top floor, the plant was on the bottom floor. That's where they manufactured them. But my office was along this side, so I had a window along the side, and Rod's office. The design engineers, the calculator guys were, I don't know where they were, but we didn't keep track of one another too much there. But anyhow, we were on this side of the building. But I wanted to introduce Jennifer here. She's back there with her husband, Nathan, and she's put together a wonderful website called team6502.org. Tells this story in 5 minutes. And I invite all of you to just check that out. I've watched it several times.
It's great stuff.
And so she's the voiceover, by the way.
Very good. Well, so where is this MOS, or where was this MOS thing? That's another story too,
It's in
right?
Valley Forge Corporate Center. Now, it wasn't in Valley Forge. It was in actually, I think, part of Norristown, Pennsylvania, but that's where it was.
Okay.
And on this side over here, right here is the golf course. So the conference room was right down from the vice president of engineering. The next few of those is where Rod and I would hang out and tell stories, waiting for the 6502 to go through the processing, and that's where Rod and I made a bet and things like this. Yeah.
So what prompted you to cross the country to go and play with these guys? What was?
It's a story. But we packed our bags and we all went together, and as a team of 7 of us come from Motorola. We were the second group of 7 that left Motorola. The first group formed Fairchild. And so Fairchild up here, and we were both sued. The guys that formed part of Fairchild, and we were sued by Motorola. They defend their information and their patent. And so we all decided, hey, we're going to quit. And the same day that we quit, August 19th, 1974, MOS Technology picked up our payroll right after that. So
neat.
Yeah, it was.
Let's see.
It was a team deal.
So I hear this Chuck Peddle guy had something to do with this move. Is that?
Yeah, well, Chuck and I would get together, and we had a meeting with the head of central research at Motorola, thinking that he taught at UCLA, I think, and but anyhow, we met with him, and then he was going to help us find a landing, a soft landing for the team that was going to do a new microprocessor. And so that's Chuck and I got together. Paul Barossa was his name, Dr. Paul Barossa, but he couldn't really find someone. So Chuck thought, hey, I have this friend of mine, John Pavinen, that he knew from Honeywell or GE Computer. And so Chuck and John Pavinen got together, and that's how that started.
Okay, yep. So let's see, I believe this is the whole gang, although this is probably from a few years later and so forth. So there you are with a little bit more hair on the left. And this is the group, many of whom came from Motorola, I guess not all, right?
Well, right. So on the left there, Will, he was the applications engineer. He wrote the hardware manual. Then myself, Rod Orgel, he was my mentor for logic. And so he and I finished the Olivetti desktop calculator CPU before the 6800. And then Ray Hurt, I went to school with Ray Hurt at the University of Arizona. So Ray Hurt was someone in charge of the process control monitor using what I did at Motorola for the NMOS depletion load. Anyhow, there's more to that story. And then Chuck Peddle, of course, he's the ringleader. We called him the ringleader. And then Harry Bauckham was a layout designer. And then Mike Janes. Mike was a very thorough layout designer, but Harry was a very fast layout designer. And the layout designers were awesome. And then Sid Holt, she was a recruit from back there. And there's a story on Jennifer's website, team6502.org. You'll find the details about these guys. And then John Pavinen, the president. I still remember our first showing up, and we went to his country club. He was a member of it. I still remember that. That was awesome. And then Walt Eisenhower was the process engineer. The person that's missing here that I think, I talked to Jennifer about this, but Don Payne, Payne, he was the guy that invented, or I don't know that he patented, but that image there that we're holding was one of his inventions or his methods, and he ran the mask shop, and he's the one that had created perfect masks. That's why we could beat the socks off of Intel and Motorola.
And that you did. Let's see. This is so in fact, many of these images we've stolen from Jennifer and her website and so forth, which I can highly recommend. So this is the MOS and management team from about 1974, 1975. Yeah. And let's see, John there is in the upper left.
The upper corner, right?
Yep. And let's see. And Payne is in the lower right.
Don Payne's in the lower right.
Payne,
yep.
Yeah.
And then there's Mort Jaffe. He was the financial guy. And then we have Walt Eisenhower there in the middle on the right. What they did with the little resources is just phenomenal. And then we have Don McLaughlin there in the middle left. I think that's right. Is that right? Mm-hmm. Anyhow, he ran the calculator guys. And so actually, they were very capable, just an incredible design group, the calculator guys. And I think the calculator guys is who built the Kim 1, not Chuck. And so that's the team. Chuck found a great team. It was a gift from the gods.
The silicon gods, yeah, absolutely.
Yeah, the silicon gods.
Yeah. Well, and you guys came in and, let's see, in a year and a half, you managed to change the process that they were doing?
A year.
A year.
It wasn't even a year. Yeah.
So what I've got here on this image, so on the left is sort of a cartoon of what the MOS folks were doing before. Right. So metal gate and P-channel devices, and you guys came in and in under a year switched it over to a very successful N-channel process with silicon gates and depletion. Depletion mode pull-ups and all kinds of crazy stuff. You're not supposed to be able to do that in a year, right? That you should be able to. It should take much longer than that.
We didn't know
right?
we couldn't do it. So you can do things you don't know you can't do, right? Mm-hmm. And anyhow, it was magical. And actually, Terry Holt, that would be Jennifer's father, who's honored with her website she created. He was part of the team that came from Motorola, and so he worked with the process. And see, because my process monitor that I created at Motorola, I split it down the middle. I had everything aligned with the crystalline structure of the silicon wafers. So I had them all lined up the same way so that I could test the enhancement mode process and the depletion mode process. So I actually knew what we could do at MOS Technology. But Terry and Walt and whoever else was on the team to create the process did an amazing job, because not only did they create it, they created a high-yielding wafer process.
To get one working chip out is amazing to begin with, but to get most of them working out, that's the tricky bit.
Motorola at the time, Ed Armstrong grew a beard, was longer than mine. Before, he was going to keep growing his beard until they got 10 6800s per wafer. Well, we got a lot more than 10 on our wafers, and I have a little beard.
Unreal. Let's see. Okay, so 1974, tweaking the processes and designing this minor little chip or something like that. 1975 comes along, and here we go. This is a museum piece. Oh, it even has the 75 date code.
Oh, good.
Yeah. So this is the real thing here, and it went over pretty well. So I have here a die photo of your baby.
Yeah.
Let's see. This should be the NMOS one, and you could ignore the. It's rather a violent thing to take pictures like this, because you got to remove all the junk on the top and so forth. So Bill did not design in the splotches on the bottom. Right. But I sort of see three sort of different types of regions of transistors here, and they seem to be sort of laid out like this. Can you elaborate a little?
Yeah, and so the data bus is on the right, the address low is on the left, the address high is on the bottom, and then the control bus that controls like the clock, the phase 2 clock generators on the top edge, and then you have NMI and IRQ and all these control pins, and you have sync on the left. But anyhow, the idea there is that in order to economize the number of transistors, we brought the opcode in, and then right above where the buffers are there on the right is where we did the pre-decode. So we didn't need a decrementer. 6800 had an incrementer decrementer, 16-bit. And the reason why they had to decrement the address is because single byte instructions, it would click over to the next address space in the program memory. And so they'd have to back it up with a decrementer. So we came up with the idea of pre-decode. So the timing generator there on the left of PLA right there is three bits of a timing generator. So we could go through timing state 0 and timing state 7. And so we had to go from that pre-decode over there to stop the counter from counting to the next.
And you're referring to the program counter.
I'm sorry, the program counter's here in the middle. But anyhow, so we had to stop that. I'm sorry. But what we also did was we could go over there and change the timing state. So I have here some things. I don't know. Jennifer and Nathan and I are going to go to dinner after this, early dinner. But I have some other things up here if you wanted to see it. We were just talking about. Yeah, some design stuff. So we called that, the top there, we did call it a PLA, but what it is a NAND gate, a NAND gate. So they're in series transistors up there. I think that's correct. Well,
let's see. So you've got it's the instruction registers in the upper right-hand corner. Is that it?
Right.
And then what you do is you pump the 8 bits of the opcode from right to left across that, and it decodes the different instructions.
Right. So we had true and complement.
Right. Sure.
And then on the timing states, we had the same. So we had so that'd be 6 lines coming this way. 16 lines coming that way. We might have had a couple extra interesting lines.
Sure, there's a few extra things, yeah.
But that control, I would call that we called that the random logic, which would take what I call the min terms at the top, and that would do the random logic. There was a guy, Will Mathis, he's one of the 4 inventors of this 6502, and we called him IBM because he did all the logic simulation. So he went through multiple times to make sure the logic was right. So Will Mathis did an awesome job.
Mm-hmm. Yeah, that's neat stuff. So I wanted to look just a little bit more at the data path here at the bottom. Yeah. And what I found interesting about this is that so you've got the accumulator on the right, the X and Y registers on the left. These are sort of the three that you get to play with as a programmer. And then the ALU's in the middle.
Right.
Why did you, the natural thing to me would be to, let's put all the registers on one side. I mean, this is how you draw them in books. What brought that on?
Well, optimization, number of lines. And so we had a special bus over here. We had the data bus, we had the address high bus, we have the address low bus, and then we had a special bus. And so we would take, if you're going to do an increment of an address, you bring the X or the Y over to the ALU, because that's where you're going to increment it, and you bring the program counter this way. So we had to look at how many lines we had to go, and if you saw the flow chart, you'd see how we were transferring things in each of the timing states. So that's what we did.
Yeah. Oh, I should give a plug. So all these images I stole from the Visual 6502 website, which you haven't seen, is just amazing. Oh, and then some madman, we saw him earlier, took that and turned it into a PCB with individual, I'm sorry, I've forgotten your name, but this is, Tour de Force. Go see his booth, 6502 with blinking lights. I mean, this is just unbelievable.
Yeah, and so at dinner last night, he said he brought the monster here, but he wasn't displaying it. And I said, wow, I'd like to see it. So then I went over this morning, and guess what he gave me? An unpopulated board. So I get to take one of these home.
Well,
awesome.
but didn't he say you had to populate it yourself, one transistor at a time?
Yeah, I'll invite him there, and I'll probably serve beer, but he can help me.
Very good. So let's see. So the 68,000 processor, I think, actually had 68,000 transistors in it, but the 6502 only had roughly 4,000 or something like that.
Maybe, yeah.
And I think you were on a first-name basis with most, if not all of them?
Well, I knew where they were and where their home was and things like that.
Yeah. Who their parents are, who their drivers are.
Exactly.
Yeah. Sounds good. So you guys released this to the world, and nobody noticed, right? It was you did a release, and there was just nothing at all, right?
Oh, right. No, that's not true. So here at the Moscone, now I don't know if I'm Moscone Center, it was a special, maybe September 7th or something like that, and so we had a suite at the St. Francis Hotel, and that was the most special. I was going to use freaking, but anyhow, it was the best weekend ever for Rod and I. We shared a few beers, maybe a pitcher, but you couldn't sell chips at the Moscone. Is that how you said it?
Yeah.
Moscone Center. We had to invite them back to the suite at the St. Francis Hotel, where there's a jar. Chuck did this. He's a showman. He was the showman. He had a way about him. You wanted to be around him. He was just one of these personalities you want to be around because he had stories and he was just a good guy. Anyhow, but he had a jar of 6501s and a jar of 6502s. Now, he claims that the bottom of the jar were non-working chips, but I think they all worked. But anyhow, we were there, and I remember Rod and I, we were hanging around because what we were doing is switching the cards, because when you go to one of those conferences back in the day before cell phones, but you'd switch and email addresses, you would imprint like a credit card on one of these things. So you'd take somebody, because they wanted a data sheet, they wanted some information, so they were doing this. Well, as it turns out, right next to us in the next booth was a pachinko machine. I don't know what they were selling, but every once in a while somebody knocked that over, and they were so upset because they have to pick up the balls again. But we went up on the second floor and looked down, and here's this crowd around our little booth. We had the smallest booth, I think, because it was a small company, small booth.
Yeah, well, just 8 bits worth, right?
Yeah, just 8 bits worth. And so what happens is we look down, and it's like when you've seen these little ants and they all looking around for their hole, right? And this is what was happening that day. It was amazing. This was the whole weekend long.
you suck the air out of all, and it was because you were selling it for so much more than every other, right? You know, how much Intel or Motorola was selling their chips for?
My memory is $375,
Yeah, or something like that.
And this was $20 for the 6501, but the 6502, the other half of that page ad, 6502 was $25, an extra $5. But what's interesting, it's the same size die, and the yields were the same. The only thing was there's a different metal layer to connect up the second phase. So it went for $5. It was a good deal, and it made it simpler to design with.
Yeah, yeah. The extra $5 lets you save an entire separate chip for the oscillator. Right. Is that
but
the idea?
Yeah, and that oscillator was going for $69. So if you got, I don't know where they came up with that number, but that's the one I remember. But it was $69 for that two-phase clock generator. And the reason why, it was hard to get the rise and fall times of the edges. So that's because I knew where all the transistors' homes were. I knew what the timing needed. So when Steve Diamond and he's the one that did the interview here of my oral history. But Steve, before and after that oral history, which was like 2 hours and 39 minutes, we talked for about 3 hours before and 3 hours after. And he says, Bill, didn't you have trouble with that? I go, no. Why? Why do you ask? It was just, you just know what the edges needed, so that the feedback from like the X register, from the output to the input, when you're loading a new value, you want to not lose what's in there, because you don't want to feed back the output from it, or you won't load the new value right. And I said, so that, we all knew what that timing was. So, but he says, well, we had struggled with that, and we had all kinds of, I said, oh, I think I know why. How many engineers did you have on it? Oh, I don't know, maybe 20. I go, that's the problem. We didn't have that many engineers, so ours worked.
It's a neat trick. So if I remember something, there was also something magical. So the 6501 was actually pin compatible with the 6800, and of course that turned into a lawsuit because everything does. But I understand there was a bet involved with a beer about the 6501 versus the 6502.
Exactly. Rod and I, he's awesome. And like I said before, magical soul there. Now he's not with us anymore, just like Chuck isn't with us, and a couple more like John Pavin and Walt Eisenhower. So anyhow, what happened was we have like 2 weeks between the times we said, okay, we're ready, go. And so 2 weeks, and then of course Rod and I, what do you do after you... What do you do now? I had some other chips to design, right, but I always had time for beer with Rod. And so Rod didn't work on the I.O. chips. But anyhow, Ray did, and I did, and Will helped out. He did data sheets and stuff like this. So what happens is, Rod and I are talking. He says, I think the 6501 is going to outsell the 6502. Now, we were both designers of both chips, sure, but I was responsible for the circuit design and the data path design and some of the critical path design, but Rod was a logician. So he says, he thinks, I go, hey, Rod, no way. I think technology wins out here. He says, I said, why do you think that? He says, because we're going to steal sockets from Motorola. They're going to have a 6800 in there. We'll just drop in this better processor in it, and, well, the 6501 will win the bet. Okay, all right. So I don't remember a dollar value. I think it was a beer value. Okay. But yeah. I don't remember anybody paying off anyway. But you don't pay off beers, you just drink more. Yeah.
Very nice. Okay, so you guys set the world on fire at WestCon, and everything starts from there. So of course it's perfectly clear sailing from that. Everything just works beautifully. I wanted to show you a couple of other things too, and ask you about this. So this is the programming manual for the 6502. Right. Who created this?
Oh, that was Chuck's. That's Chuck's responsibility. So when you read the programming manual, get in touch with Chuck there. But Chuck, he had a lot of things on his plate, right? He's going to change the world with this little microprocessor, but that means that he's being distracted a lot. So he wants, and also Chuck likes talking and telling stories. So he's the marketing guy, right? But he's also a systems engineer. He's not a semiconductor engineer. That's why he recruited me and Rod and Ray and the mask designers. So, but Chuck, we had to basically lock him up and put sandwiches under the door of some motel and say, you got to finish this before we'll let you out of that. We've got you locked in. But anyhow, I don't know how much that really is true, but that's a little mythology maybe. But anyhow, Chuck is the one that wrote that, and he did a good job on it.
And he was largely responsible for the ISA design, the instructions and...
The instruction set architecture, if you want to do something, you probably have in this museum a PDP-11 programming card. Check the PDP-11 programming card and the 6502 programming card, or the instruction set. You'll see that they're named the same for some of the instructions. So actually, you build on the shoulders of giants. That's what we did here. So we already knew microprocessors. Rod and I designed two before the 6502. So we knew the Olivetti, which is awesome. Mostech sold it as the 5065, but that was a desktop calculator for Olivetti. But what you do, and what Chuck was, he was going to pick out the instruction set, and Rod was there, and Will was there. And, did I work with them on the NMOS? Maybe, but I wouldn't claim to have. I was busy trying to make sure the transistors were the right size. And so so Chuck was the sign-off. He was the sign-off. So if you look at the first programming card for that, you'll see ROR is missing. ROR was added. It wasn't a mistake that it wasn't in the programming card. It wasn't part of the design. So when someone talked to Chuck about, hey, we need an ROR, oh, okay. So then we had to put it back in. Now we had to change it, but that it worked the first time.
Pretty neat. And so I understand you ran out of sandwiches, and so somebody else had to do the hardware manual. Is that?
Yeah, the hardware. Wow, getting the software out of Chuck was.
Yeah, you'd already pulled all the teeth you could.
Yeah,
so,
right,
yeah.
right. And we ran out of sandwiches.
Right.
But anyhow, the hardware manual was written by Will Mathis. Will Mathis, as I said, we called him IBM because he did the simulation of the logic. And so he wrote this hardware manual. So the challenge right now that I haven't looked at, I have copies of these in my little museum back in my office. It's co-located with my office, which is functioning office. It's kind of like Intel. Intel has a museum, I think, in their office, and I saw a picture of it, and it's a pretty awesome museum there. But anyhow, if you send me where you found set overflow mentioned in the software manual or the hardware manual, because I'm wondering whoever used it.
Yeah. So far as I can tell, exactly nobody. But
well, you might want to know a little bit about that, the set overflow. And I wanted to mention Nathan is Jennifer's husband. I forget the name of it, but I'll find out to get the name. But he's for saving pets' lives. And so set overflow is really, the backstory is it's Sam Orgel, which was Rod's dog. And that was what Chuck and Rod and I knew, and Will knew. SO was really Sam Orgel. But so set overflow was the way to get an input into the processor to quickly, you could branch then on that pin by setting or having overflow set or cleared. And so we have some branch instructions. So it's a way of fast I/O, but I don't know if anybody used it.
Yeah, it's one of the most mysterious pins on the NMOS 6502. Well, I think it disappeared.
There's one other little story. So the Visual 6502 guys called me, and I think it was about set overflow. They said, "What is that? What's going on there?" And I'm going, "Oh, so now that is written up in Archaeology magazine about 10 years ago." And when the guys from the Archaeology magazine called me, and I said, "Hey, I have a little story. It's like in the pyramids when you're digging for some things, and maybe a mummy over in the corner goes, look over here. There's something interesting over here. But that never made the article, but I remember talking to the
I thought it was like calling up Imhotep and saying, hey, dude, what's with the steps? What's the,
yeah, exactly.
What's the whole pyramid stuff?
How'd you do those big boulders anyway?
Yeah, exactly. What was the trick there? Secret. Okay, so now we're on to 1976 here. And so MOS technology is going to take over the world, or what happened in 1976
what
here?
happened there? The team disintegrated. I think that's when Terry may have left. But I think it was Rod or somebody, it wasn't me, that discovered Chuck's terms that he agreed with the team moving was a percentage of the profits, because we had dreams of becoming wealthy like Elon Musk or somebody, or Bezos. But we didn't. What happened was, at one point, maybe over a beer, maybe Rod figured it out. He goes, wait a minute. When will we ever have a profit? I go, oh, yeah, I didn't think about that. So anyhow, but I don't know if that's what caused the disintegration of the team, but Terry left, Rod left, Chuck left in 76 when Commodore took over. I wanted to do general purpose things like the PIA, the VIA, the 6530 chip, the 6502, 65. These are general purpose. But Commodore wanted to build game computers. And so they have this great set of chips for sound and video. And Al Charpentier and I talked about things like this before but I was out of there in March of 1977.
Okay. Sounds good. So, so 1978 here. This is sort of an odd juxtaposition. We've got it's just the usual thing. The Las Vegas hotel, the dunes, we think, and we've got looks like maybe a prototype calculator. That doesn't look like a production model to me. And so you had told me something that these two are actually connected somehow, and I can't figure out how you could ever possibly do the connection here. So what's the story here?
Well, the story is on Mother's Day weekend. It would have been a Saturday. Mother's Day is on a Sunday. Chuck called me earlier in the year, about February of 78, and said, Jack wants you to design calculator chips for him.
Which Jack is this?
Oh, Jack Trammell.
Jack Trammell. Mr. Commodore, not Jack of all trades.
Whenever I use Jack,
he was Jack. Okay.
He's just Jack. But anyhow, Jack and I and Chuck met at the dunes. If I've got the right
Right.
casino.
It's hard to remember that, and there's so much neon involved.
Yeah, exactly.
And probably a little bit of alcohol.
Well, what happens is I show up because I said, hey, it's Mother's Day weekend. I can come up there for a couple hours and not fly back because I want to be there for tomorrow.
Yeah.
So I'm not going to stay over. I didn't gamble. I may have gambled leaving in Motorola in August.
Yeah, that was a pretty good gamble. Yeah. Paid off. Paid off.
I won the bet. Anyhow. So Jack is down by $10,000 when I show up at the table finding Jack in a casino. I don't even know how you do that. Wasn't cell phones then. But I did. I found Chuck, and Jack is betting big. Chuck has got a few little chips. And so I show up. He's down by $10,000. And then he makes these big bets. It's like you kind of gasp. And he's up by $17,000. He says, Bill, maybe this could be a good time to talk. So we went to his room, and we talked, and he offered me a division within Commodore department. Whatever I wanted, he wanted to offer me. And then he added in a kicker. And Chuck's sitting here, Jack's here, I'm here, and he says, and I'll pay you more than I pay Chuck. And at this point, I see Chuck's eyes light up like this. And, what? But anyhow, I said, well, actually, Jack, I want my own company. Okay. Well, how are we going to do that? I said, I'll write we'll have a contract, and there'll be milestone payments, and I'll make all of my profit on the royalties from the chips. So I want you to be successful with my chips. That's the deal. Shook hands. I left. He went down, probably wanted some more money. Oh, so that's the scientific calculator. So that top is what Commodore, that was a scientific calculator. There's like 16 characters on there.
Yeah, LCD, yeah.
Yeah, and then that's a prototype of it's a 4-bit RISC processor that could do nibble based. So you could have 4-bit, 8-bit, 16, all the way to 64-bit. And Shiraz Shavi, who wrote the code for it, he worked back at MOS. I thought he was always out here in California. But that's the scientific calculator. I have it in my display case. I think when David Gray, who works for me, David Gray's a mini-me, but he's 6'4", and he's a big guy. But anyhow, David Gray is my go-to guy for everything these days. But he put some batteries in there, and he saw some things show up on the display. There you go.
And so the chip here was one that you at Western Design Center, I forget whether we got the name of your company in there.
Oh yeah,
or that you formed. So that was one of the chips you would design sort of on Jack's behalf, or for Jack.
Well, there was one that came before this. It was Toshiba was the leading company in Japan in CMOS calculator chips, and Jack was losing his calculator business because PMOS was too powerful, used too much power. So CMOS was the name of the game. And so the design engineers, the calculator guys, designed with PMOS, and PMOS is lower power than NMOS. Those are usually serial, 1 bit at a time, ALUs, keep the power down. But anyhow, so 4 bits at a time was going to move Toshiba out of the business with Commodore's great marketing of calculators. Well, as it turns out, all Jack wanted was to go back to Japan. I think his son, one of his sons, Leonard, or somebody was back in Japan and was a marketing guy. So Jack just said, hey, we'll just show Toshiba that we can build our own calculators, or maybe they'll give us the Japanese price for calculator chips, which was half of his price. So what he did with my designs was negotiate with Toshiba to get a lower price for 5-function calculator chips and scientific calculator. So he never really, he got the prototype working, but that's all he wanted to do anyway. So there you go. That's the story.
Wonderful. It's truly painful. This is why I left industry to go to academia.
Oh.
I kept designing stuff, and they said, "Oh, that's great, garbage can. Oh, that's great, garbage can." Anyway, okay, so 1981 here, I had a great time finding these slides, right? Things changed again. You picked up a phone, from what I understand, right? And that's somehow the next chapter in WCC. Right. Uh-huh.
I like your humor. I follow Steve on Facebook, and he's got the most humor of any professor in the world, and I just love his humor.
You need to follow a few more professors, but yeah, no, well, I appreciate the plug.
Well, but anyway, yeah, okay, that's a Intertel telephone, but this was really what changed my life, and GTE is one of those companies that just fantastic. I'd have to say, if there's one company that I love more, it's Rockwell. Rockwell's just, anyhow, that's another story. But anyhow, GTE sent me to Belgium, where they had an ATEA division in Belgium, and they had already licensed the 6802 from Mitel and the process. And it's an oxide isolated process, unipolar dope process. I reverse engineered all of the popular processes in 1 year between leaving MOS, going to IC, Integrated Circuit Engineering, and then starting my company, Western Design Center. But what happened is I knew that what RCA was doing in CMOS, which was insanity, they had circular transistors and all these other things because they couldn't shut off the channel. Oxide isolation shuts off the channel. But unipolar dope meant you didn't have to go from the P-channel transistor to metal over and then down to the N-channel transistor gate. Unipolar dope poly said you can run poly straight across everything, no problem. That's what happened here. So when I went over there, see the 150, 65 SC 150? The 150 was a one-chip system where when I came back from Belgium, they wanted me to quote on a 2-chip system, 6802 plus another chip. I came back and said, we can put it all on if you throw out the 6802 and put the 6502 in there, which did not exist. It wasn't built. So the first chip that was designed with the 65CO2 instruction set was the 150. Then I took the core out of that, and that's how we got the 65CO2.
Yeah, so I have here the block diagram of the 65 SC150. This was the thing that came out, and what we still in love today is the 65 CO2 and the 65 816 all stemmed from this chip, and you sort of sneaked it in about it.
Yeah.
I like it. Yeah, it's nice.
Yeah. So SC, GT called that silicon gate CMOS. I thought of it as slow CMOS. So then I had an FC for a while, and then I made it C because Rockwell just put a C in there. Hey, it's CMOS.
Yeah, that's fantastic. And so this somehow begat and eventually begat the 65C816 and all of that stuff as well. But I thought that was an interesting story that somehow you didn't really set off to do the 65CO2. It was more, oh, well, how do I keep these people happy? And oh, by the way, I'd love to design a processor as a side effect.
Right.
I like it.
Right.
I like it. So we've got some slightly more modern stuff here. Apparently, I was noticing on your website you can go and buy your own Mensch.
Right.
These days. Okay. Yeah.
Then,
so what are we looking at here?
And then you can make it your own, and now we have my Mensch. And my Mensch, that black chip there in the middle of that is a Intel chip. So Intel and WDC get along just fine these days. Intel spent $32 billion on acquiring Altera. So that's an Altera Intel FPGA. It's a Max 10 M08. It's an M08 SA chip. SA stands for, the A stands for analog. So it's got built in an analog to digital converter. And so what we have in there is a 65 CO2, 3 VIAs, 3 ACIAs, I2C, SPI, 172K bytes of flash, and about 64K bytes of SRAM. And so we can bootload the SRAM from either that black connection there as a USB, so you can either bootload from a PC or bootload from what you have in flash. That screen up there is... I don't know if it's showing it right now, but maybe the coordinates for the latitude. Oh, maybe. Anyhow, that's that's a GPS radio there. Those connectors are out of Europe. I don't know if it's Bosnia or where it is, but those are click connectors. So a click connector, they have about 800 different modules we can plug into that. So the reason why we did it this way is so you could write code for GPS, crypto chips on it. They have all kinds of things. It's Microelectronica is the company. And everybody in the industry has little modules that plug into that. So we can plug into all kinds of things. Then on the left here, those 4 are Grove connectors from Seed Studio. They're out of China. This is international board. And then we have SparkFun. Oh, it looks like it's cut off. Up on the in that corner there is a quick connector, QWIIC from SparkFun. So those are I2C, and we also have some fun things there on the VIA. We have that has the serial interface on the VIA. That was used originally in the Macintosh mouse interface. And then we have 2 VIA pins there. But we can connect anything in the world on that little board. We call it the Pro for prototype, short for prototyping.
Yeah, that's fun. And you've got a whole bunch of... This is great. I love the fact that the 6502 has continued and multiplied and changed a bunch of things. Oh, yeah, actually, no, you didn't put a hardware multiplier in yet. But
we have a hardware multiplier and a hardware divider.
Okay. I'm behind the times. This is embarrassing.
I thought this is part of your humor.
You can't tell anymore. No, people can't. Anyway. Let's see. So I've got another bit of semiconductor porn here at the end. So this is a utterly unremarkable looking wafer at first, right? But there's actually something sort of magical about these wafers. Can you tell us what these are?
Yeah, those are the first 65CO2 functionality on NMOS thin film out of Edinburgh, Scotland. And the team is also in England, near Cambridge. But anyhow, we're partnering right now. There's a company in Belgium called IMEC, I-M-E-C, and they're a big conglomerate or whatever. They're big. I don't know that much about them, but they do multi-project things. Like USC had MOSIS, M-O-S-I-S, for multi-project for universities and research. So you could build several different kinds of chips on the same wafer. Well, this is a thin film wafer, and so if you go into next time you go into the meat department of your favorite grocery store and you see the meat wrapped in a cellophane, you can put now labels on them. We're going to build the 6502 into sensing labels and all kinds of things. In fact, the partners that we're creating, they think we're going to sell trillions of 6502s on everything on planet Earth, Mars, if Elon Musk has anything to do with it, and the moon. We're all looking for the moon, I guess, for rare materials for our cell phones. But anyhow, the point is, everything's going to have a label on it, and we think the 6502 is going to be part of that. This is much smaller. They also have an ARM in the same technology. They just got these out this last month, so this is hot off the press. I talked to them, and they sent this so you could show them today.
Yeah. This
has not been announced yet.
Yeah, so it heard it here first. And, well, the hope is that on a per-die basis, it's going to be just absurdly cheap, right?
Yeah, I'm talking about a penny is a high number.
Right, there we go. Okay, so, a penny is 6502. That's pretty good. You might even want to, gang 4 of them together and get 32 bits worth.
Well, the other thing, we're here in Waz territory. By the way, every time I go to my hotel, which I'll do it again, I come and go on Waz Way. And it's so special. I see, take Roz Way on my GPS. Yeah, sure. I'll do that. I can do that.
Yeah, it's pretty good. Yeah, and well, let's see. These are also flexible, so you can bend them around.
Oh,
right?
yeah.
They're something like that.
It's like when you look at these little things you see every day now, if you have TV on, where you see these little bottles of vaccine, right? Well, you can wrap this around there, and you put all the information you need right on there. And with the 6502.
Great stuff. So, continues to live on. Let's see. I was going to correct. So, he was saying earlier that 6502 spoiled his grades. It actually made my grades in high school. So,
well, that's good to hear.
Nice
it helped somebody out.
Yeah. One or two of us appreciate what you've put together.
Yeah, but he had a tongue in cheek there.
Yeah. It's hard to say. My sarcasm too. It's years ago. I had a roommate who liked to confuse his girlfriend. We had very similar, and would say something like, "Would you like hold up a sign or something when you're being serious? Because I can't tell anymore." It was really a problem.
Well, the reason why you don't have a sign is because you're never serious.
There you go. Let's see. So this is the end of what we had prepared for. So this would be a great time. I, of course, have plenty of additional questions, but I'd love to hear from the audience at this point. So let's see. I guess there's a mic that can be passed around.
Well, no, it's COVID. We don't pass the mic around.
Oh, okay.
I'm the virtual mic.
You are the mic. Okay.
I am the mic stand.
Okay. Yes.
So, are there any questions? Please raise your hands. Okay, I'm going to try and get one at a time here. So hold on. Got to get you on mic so we can hear you on the recording.
So a friend of mine, I mentioned that I was at the show to a friend of mine, and he wanted to know how you feel about the fact that your chip is still in use and there's all of this amazing homebrew software and stuff that's pushing these to the absolute limit. How do you feel about that?
I feel awesome about whenever I hear somebody's either copying it, don't tell me, Alec here created the Monster 6502, the Visual 6502, all these things people are doing with FPGAs and creating their own cores. I just love it. I just love it, and it's what I call a timeless architecture. That means it's going to be here for all time. And that's because it's just a very economical use of 8 bits at a time. And I just love that. And the creativity, if you take Wozniak out of it wouldn't be what it is without Wozniak. And of course, then, if I don't include Steve Jobs, I mean, come on. Come on, man. I mean, this is just good stuff. I'm trying to unfold the 816 layout because I want to show you something.
Let me help you with that. So I hope you don't have a telescope. This is all highly proprietary.
First time out of the cage.
Good thing I'm recording at 16K video.
Yes, it is.
Well, you try to figure this out. I wanted to say, this is the only 16-bit processor ever designed.
Microphone? I got it.
Oh, yeah.
You need to hold.
This is the only 16-bit microprocessor designed by one brother and one sister. My sister designed that. We did it in about 1 year.
Yeah.
So that's 16-bit. This is fully static. These are the static holding devices. And when I asked her to do that, I thought it was impossible. She couldn't have done it. I design, I can do layout, but I have other things I do also. But she did that, and I thought, how did she do that? I still don't know how she did that, but she did it. But anyhow, I wanted to show this off. There you go. She worked as a consultant after leaving Western Design Center about 20-some years ago. She worked for Intel for a while, for 6 months, but as an outside contractor, and then Qualcomm. And then Qualcomm made her a deal she couldn't refuse, so she no longer went back to Intel. But she set up some design center in India and other things. There you go.
So one of the things I wanted to ask you about was, so we've got the same rough layout where you've got the instruction decode at the top and then the data path at the bottom. The data path looks like an 8-bit data path. I'm sort of seeing 8 channels. What's going on there?
It is 8 channels, and for 16-bit, I put them side by side.
Ah, okay.
So look ahead carry for the program counter. I only have an increment, I own a 16-bit program counter, but I can make a 24-bit address out of the bank address. So I had 24-bit addressing. Intel could only do like what was there? Oh, 1 megabit, 1 megabyte addressing, but mine could do 16.
Yeah. Well, Bill Gates said nobody need any more than the 640, so it doesn't matter.
Yeah, and then they changed that, didn't they?
Yeah, I think he came to his senses.
Yeah. There you have it. This has more than 8 timing states, so that we have a 4-bit, so I could have 16, but I don't use 16-bit timing states. I have the flow charts up here, but I think we want to go to the questions again, right?
Definitely, yeah.
Okay, so raise your hand. I think there was one over here from earlier, and then I'll come get the person over there.
Thank you. I have a question about page 0. How that idea came over in the design, and do you try against having multiple registers like the Z80 or other registers? Because that was a very, very high end that was outperforming other processors that were supposed to have more registers or more power.
Okay, are you saying page 0, right? You're talking about page 0, right? Yeah, I named the architecture, actually Chuck and Motorola, it started with Motorola, they called it memory mapped I/O, which it is. And that it's like this is a von Neumann architecture. And von Neumann architecture is, as opposed to Harvard architecture. Now, they should have called that if they have a Harvard architecture, then this should have been a Princeton architecture. But instead, it's von Neumann. I guess there wasn't a guy at Harvard. But anyhow, that they could hang it on. So page 0, I call this architecture, what do I call it? Oh, addressable register architecture. So that means page 0, you can build registers in page 0. So like for instance, we have a tool suite, which is a assembler, C compiler, and libraries. And our libraries are the we have floating point libraries. And those floating points, which is 8 bytes, 64 bits for floating point, you can build that in page 0. So we have page 0 registers, so you can build them. And in fact, on the 816, I extended the page 0 with a page 0 register. So now you can build 256 page zeros. So you can do a lot more. Now, of course, ARM came along. They wanted me to help them design it, and I said no. There's a guy here. I just heard the name. Now, I know somebody here knows the name, but Doug Fairborn is he's the photographer here. I don't know if he's still doing that, but he did the layout of the original ARM for the Newton project, and I got more stories about that. But anyhow, that's what we were doing there, and so we wanted to make page 0 high performance. That's why if you do things in page 0, you save a cycle.
Did the 6800 have the notion of a page 0 as well?
I think they did, but also the other interesting thing is that the Olivetti chip had page 0.
Ah, okay.
But the way that Motorola, Mike Wiles, you'll see his name on most all the patents of the 6800. Mike Wiles was taking a graduate course at ASU, and they had a PDP-8 in there. And so the PDP-8 is where the 6800 come from, and I think the 8 came from PDP-8. We didn't want to use 2 digits, or it would be called the 611 or something because of the PDP-11. But what I was going to say is the Motorola wanted the engineers to be able to read the address, the printout of your assembly, right? So if you did that, that meant that you picked the address high byte, you picked the opcode, the address high byte, then the address low byte. And what's interesting about that, you can't do anything with the address high byte. But we do the opcode, 6502 does the opcode, followed by the address low byte, followed by, if you go 16 bits, address high byte, and if you're using the 816, the third byte of the address. So what you can do with this is you can increment, or you can add to that with an 8-bit index register. So you can start working with this, or you can just throw it out on the bus. And so what that means is that we're faster, a lot faster than the 6800, and that's why we did it with the minimum number of transistors, the minimum number of cycles, and it should be fun, and it's attracted a lot of love.
Yeah.
That's what I know.
So there you have it. This is the resolution of the little endian versus big endian debate. Of course you do little endian, right? You know, the big endian people don't know what they're doing.
Right. Yeah, I don't know which is which. I memorized that, and that's one thing I'd fail on your test, actually.
Yeah. Well,
so don't ask me that one.
For years and years, I was explaining, you can do them either way, and it works either way. But now I know, no,
it doesn't.
In fact,
so what is the 6502?
It's little endian.
Okay, yeah.
Yeah.
There you go.
It's backward from what you'd expect, but it's that's the right way to eat your egg.
Oh, is that?
Or something like that. That's the debate.
Yeah, well, debate's over for me.
Yeah, well, it was for me too, but then I figured it was just because I was brought up in the 6502 ecosystem, and it could be separate but equal. But no, as I figured, we had it right all along.
Right. So when you look at it that way, that's why I call it a timeless architecture. Addressable register architecture. Now just think if we were running at the same speed as the Raspberry Pi, right? Or our cell phones with a 6502, with memory address registers, or addressable register architecture.
You'd want a little bit more memory. You'd want a few more address bits.
Actually, what we do on the Max 10, it's built for the 32-bit. So we have a 32-bit interface on the memories on the Max 10, But we're just as efficient as a 32-bit when you want to get something done.
Sure, sure.
But we can do that. So we know how to work with 32-bit or 64-bit or 128-bit or 256-bit. We can work with those.
Yeah, pretty fun.
Okay, there was one other question back here, and then I'll come up here. So hold on, coming down.
Uh-oh. Hey, I see.
So I'm curious about
Eric.
1973, you, RCA with the 1802, Zilog, everyone seems to have come out with chips within, 6, 8 months of one another.
Uh-huh.
What was the magic there that was the year, and why couldn't it have happened 2 years sooner? And were you all trading jobs so that the knowledge went from company to company, or?
You know, I don't know, but certainly it went from Motorola to MOS technology. We know that, right? But it's like right now, I'm driving a hybrid for the first time. Where do all these electric cars come from? And see, what I'm getting at is I think once the business people, the investors say, hey, we need a microprocessor, I think everybody said, we need a microprocessor. Intel came out with a 4004, and we all need microprocessors. And Doug Spicer here did a chart, and I reintroduced him to his own work earlier today. And he's doing an article on the microprocessor because 50 years ago this year is when the first microprocessors were, I guess, sold by Intel. But anyhow, I think that stimulates the investing community. I think it stimulates the engineers coming out of Columbia or other schools
Other
back
minor
there.
schools, yeah.
Yeah,
There's one or
and so what I'm getting at here is I think the answer to your question is the time was right.
So processes were being, big changes in processes were happening about the same time in semiconductor processes, right? So
Yeah,
the depletion mode, the enhancement mode, is it CMOS, is it NMOS, or something like that?
Yeah, it started out, actually, field effect transistors, I think, were before bipolar. And so the process, the MOS processes went from PMOS. Now, as it turns out, these pictures of these thin film, they're NMOS transistors. They don't know how to do thin film PMOS transistors. So it'll be a few years before we get the CMOS approach to this. They're working on it. They're going to figure it out, I'm sure. But anyhow, the line widths here is about the same as what it was when we designed the 6800 and the beginning of the 6502 in NMOS. So the technology and the wafers, and Moore's Law, I think it started in the 60s. Now Intel's reinventing the words, but the technology can't go any further with the Moore just shrinking it. Now they're calling it angstrom technology here at Intel, so that they can fold all kinds of stuff into that. So it's really more about the architecture of the semiconductor processing rather than the finer geometries, because at 5 nanometers, you're pretty small. That's only about 10 atoms, I think.
Okay, there was another question in this general area. Okay, coming on over. I feel like Vanna White.
So the
You don't look like her.
Certainly don't.
Thank you for the presentation. The question I have is, everybody's, of course, moving to 32-bit. 32-bit's going to be the architecture of the next century. 64-bit. So the question is, what would a 64-bit 6502 look like?
I'd say it looks like ARM. I'm a big proponent of ARM, as you might be able to tell. They followed my business model. They came and visited me in the fall of 1983, wanting me to design their first ARM, and that's where Doug Fairborn, because I said, well, there's other people, and VLSI Technology is where Doug worked for. So, Alex, coming back to your question, I don't think you want a 64-bit 6502, because what does that mean? Now, I could, and I have specified, I don't know how many, half a dozen 32-bit processors, and every time I did, I'm going, you're going to need a few hundred engineers to really accelerate it. and that's what Intel has. You know, how many engineers do they put on a project? They have multiple teams so that they can bring out a new processor every couple of years, but that means they have a few hundred engineers on each of these teams. My nephew, who worked for me, got his engineering degree from ASU, he worked on the Pentium Pro. 200 megahertz is what I remember. He thought I was crazy when I said in the programming the 65816 that we'd have 100 megahertz chip someday. And of course, when he's working on a 200 megahertz Pentium Pro, then you go, yeah, oh, I didn't know. And now what do we have? I think Intel's up to like 4 gigahertz or something like that now.
Yeah,
so
except they
I don't
stopped.
think you want a 6502 in a 64-pin package because there's so much software, there's so much other things. And just enjoy what you have.
Hey, thank you so much for the presentation and for your work. I'm one of the people who cut their teeth. You know, that's how I learned to code. And coincidentally, I also worked on the Pentium Pro, but that's another story.
Oh, yeah.
But my question is, you know, given the wild success, the number of proliferations, the different applications, if you had 100% knowledge going into the design of all that was going to follow, are there any design decisions that you would have made differently?
Good question, and thank you. I've had a lot of time to think about that, especially when I'm trying to design a 32-bit processor to compete with Intel and ARM, and then recognizing no, I did it. I did what I wanted to do. I mean, you know, there's some features right now in the 816 that one of the engineers that works for Microchip now, he worked for me for a few years. I don't know, Chuck and I had a long relationship from about 1973. I started at Motorola in 71. So I started at the beginning of the microprocessor revolution, right out of University of Arizona. So Chuck came in 73. So he came, what appears in the rearview mirror, he came to raid Motorola, and he did a good job. And that's where the 6502 came from. And so he freed me from that because they were trying to move us to Austin, Texas. And we had family near Austin, Texas, and it'd take me 2 days to drive across Texas. And Texas is kind of flat. So I have a home in Durango, Colorado, and when it's hot in Arizona, I'm in Durango. When it's cold in Durango, I'm in Arizona. So I have self-induced climate change. And so I like that. They're called snowbirds if they come from Canada, but into Arizona. So coming back to your question, the stack processing mode that I put in the 816 has never, I don't think it's ever been fully used in a compiler. And that idea came from a student that graduated from Princeton. He was the son of Larry Hittle. Larry Hittle should be mentioned here because he's the one that built the emulator for the original 6502, working with Chuck Peddle. They both worked with John Pavinen, MOS. Chuck and Larry and John Pavinen worked in GE Computer or whatever. Larry set up, I think it was Dartmouth, with their first time sharing. Larry Hittle was the president and founder of Courier Terminals, which was the first terminal company for time sharing. And so all of this technology is there. So your question, I've been around great architects, great people. This technology came from them. There you have it. You're welcome.
Got one more question here, and then I saw there were a few over there, so.
Two things quickly. First, WestCon 75 was at the Civic Auditorium. Moscone Center wasn't built yet. But I was going to recommend that you look into RISC-V. You don't have to pay ARM $40 million to build a RISC-V chip of your very own. And it's we have 20 people at our company. We did 2 different RISC-V cores for our chip.
Yeah, I recommend RISC-V. RISC-V is awesome. And the team that built that out of Berkeley, now the guy sitting next to you have Berkeley shirt on, right?
It's not my team, but I work with those guys, and they are brilliant.
Yeah, and that's what was needed. So the RISC-V is what was needed. So I had thought that we go from 65 to RISC-V. I think that's a good thing to do. So yeah, I'm a proponent of RISC-V. Now, that means that my ARM friends, by the way, this plastic stuff is invested by ARM, and so ARM and WDC, they know how to work together. Intel and WDC, even though Intel doesn't know I'm doing this, not at the corporate level, but hey, we're just using their good technology, Altera technology. So the RISC-V, that's a good thing to bring up. So there you go. That's the answer to the 6502 at whatever bit width. Go to RISC-V. I mean, you have an advanced IP business model there. And so that, I think the Chinese are adopting RISC-V as their... Yeah, and so what can I say other than I recommend ARM, I recommend RISC-V, and I think RISC-V is going to change the world, much like some of these other earlier processors did. And I think it's because of the business model. I think it's because of the freedom of technology. I started Western Design Center. I put the business plan together, and I was going to start it July 4th, 1976. Freedom of technology. But then I didn't know what I was doing. So then I worked for a year for Glenn Madeline at ICE, reverse engineered all the processors for Romaire Development Center. And so then when you see all these processors, then I knew the 6502 was the winner. Because the TI 9900, I2L, integrated injection logic, that was amazing what TI did there. And the Z80 and the 8080 and, all these processors back in the day. 1802, that's how I got to know the 1802. For $5,000, we reverse engineered and had to produce a report for the Romaire Development Center so that they would be able to use the best processor. I don't think the 6502 was actually in the group. But thanks for bringing up the RISC-V. RISC-V is awesome.
Okay, there were some questions over here. So let's go over here first. Pardon me.
Oh, right. Gotcha. Sorry about that. So I'm a developer on one of the many 6502 compiler projects for C. Depending on who you talk to, there's been kind of an enmity between C and the 6502 due to C's really heavy use of stacks and 6502 having more expensive stack addressing modes than absolute addressing modes. So I was wondering if C was on the radar when it was being designed, or if that kind of programming style wasn't in vogue yet.
Okay, thanks for the question. C wasn't around. C wasn't around when we did the 6502. There was a professor at the University of Arizona that worked for me for a summer. His name, I think, if I remember correctly, was Ted Williams. He taught compilers. He said to me, I think you ought to look at the C for your 816. That's why I asked Larry Hiddle's son, Paul Hiddle, when he came out. He worked for me for a little bit also when he was going to the U of A. He got his master's from the U of A in a year. Very brilliant kid, man. But anyhow, that's why I put the stack addressing modes in the 816, and I have a 16-bit stack pointer, so it's a lot bigger, 256 times the size of the CO2. But going back to your question, the compilers, the 6502 and compilers, I smile because when you want to get something done, you write it in assembly language because you want the machine to be most effective. It's like if you want to talk to somebody in France, you'd use French. But if they have to do the translating while you speak in English, then they can do that. People can do that. But this means that a high-level language, if it isn't as effective as an assembly, meaning manually optimized, then it's the human mind in competition with the algorithms for the compilers. So actually, the 6502 was never meant to be a computer. And when I suggested in the fall of 1973, when my wife was about ready to, at the time, give birth to my first child, is when I came up with this idea that, wait a minute, you could take a 6800 and a PIA and you can build a little home computer out of it. This was the time when Hewlett-Packard was coming out with their calculator, HP 35 or whatever the number is. And so you see what happens here is Chuck and I knew that we were going to build a microprocessor as a controller processor, microcontroller. It wasn't for computers. And when I said to Chuck one morning, walked in there, and I still can see the little bathroom. Then when I came up with this idea of a home computer, this was in '73. And so what happens is I go in there, and Chuck's standing next to me going, we're not doing computers. We're not doing, and he was like trying to intimidate me. And I don't know, when I asked him years later in about 2007 why he was doing that, why he was trying to intimidate me, I said, I wasn't going to do the home computer. I was perfectly happy being an enabler with chips. I'm a semiconductor engineer, enabling other people to build the systems like the Wozniaks and Nolan Bushnells and the Chuck Battles of the world. And so I'm just happy being there. So coming back to the C compiler and think compilers, C compiler, I don't know when it came out, but I think it came out or it was available in a big way after we had the 6502, but I wouldn't have changed a darn thing. There you have it.
Okay, we've got time for one last question. Okay, since I'm standing right here, this is you, sir.
Speaking of assembly language, the 6502, as opposed to later processors, does not use microcode for the instruction decode. Instead, it's all hardwired in silicon. But that gives rise to, if you use opcodes that aren't documented, you get additional functionality that is not documented. And some of those actually carried over from revision to revision of the 6502. Did you foresee people experimenting with those? And if so, did you plan for any of this undocumented functionality in the chip?
Thanks for the question. No.
We call those Easter eggs.
Those are Easter eggs? You mean the question is an Easter egg?
No, that's a rotten Easter egg you're thinking of.
Easter egg instructions.
Oh, I see. Yeah, you know what? When I first read about that, in a magazine article or something about the undocumented opcodes, I'm thinking, are you kidding me? Someone actually tried to use an opcode that we didn't design for. That's weird. So when I did the CO2 and the 816, I used all the opcodes, and I named one WDM on the 816, and that was supposed to be the gateway to 16-bit opcodes. But I never did that. But the WDM was a byte that'd be the first byte in a 16-bit opcode, or a 32-bit, or whatever you want, or 64-bit. But I didn't do that. So the answer to the question is, I was surprised. I'm surprised a lot, but the point is that why would anybody try to figure out what the undocumented opcodes? We didn't know what was going to happen, and we didn't care what was happening. We just wanted to make sure what we wanted did happen. And so when Alec builds the monster, you go, who would ever build a monster 6502? And you go, people do the interesting things. And so your question is about the creativity of people looking at things in a different way. And so if somebody's complaining about, well, we could have done this with the unused opcode, well, I did a lot of things on the 816 with the unused opcodes.
So following up on that just briefly, had you done something with those undocumented opcodes, what would have happened to the die? It would have gotten bigger and slower and all the rest of that?
Well, it got bigger and probably slower because there's more transistors to move around,
exactly.
More lines to move up and down.
So it was more of a logic optimization thing to just leave those out entirely.
Yeah, exactly. And to do what I did on the CMOS version, added logic, because I wanted to... I thought people were complaining about the unused opcodes. So all the unused opcodes are no ops. That's what I did on the CO2. But now it took a lot of fun away, right? I mean, I guess I could probably, no, I wouldn't do that.
Maybe that's what we can do. What I can do is ask you to design part of a processor, leave out half the instruction set, and you could leave the rest of it for us to figure out again.
And see what happens, because I didn't decode it, so tell me what happened.
Yeah, exactly.
You can have fun with that.
Yeah.
Yeah.
Very good.
Well, I think that's all the time we have. I really want to thank you guys. Can we give a little bit of a round of applause here for these guys? Great discussion. Great discussion.
Thank you. Thank you. Thank you. Thank you. Hey, I want to know, I want you to know this is my life. I think you know that. So thank you. Yeah.